All right, we're going to be going over decimal to hexadecimal conversion. So before we get started, just a little bit of recap. This might be obvious to some who have seen the other videos, but I'll just go over it anyway. So decimal number system is base 10. And what that means is that it is made up of the following values, where it is 0, 1, 2, 3, 4, all the way up to 9. And then hexadecimal numbering system is base 16, where the values that we have are the same as the decimal up until 9, and then we have A, B, C, D, E, F, where A is 10, 11, 12, 13, 14, and 15. Okay? So I'm just going to go ahead and start with a few examples. I think that is best way to show how to do this. So if we take a number like 45, for example, okay, what we're going to want to do is we're going to want to turn it into a binary number and then break it into 4-bit chunks and then turn that into hexadecimal. So it's like a four-step process, quick and easy. Okay. So let's say we start with 45. Okay. We're gonna want to turn that to binary. So once again, we have our weighting. So 1, 2, 4, 8, 16, 32, 64, and 128. This is 8 bits. We're not gonna need 8 bits for this because, well, it's less than 128. So as we get started, we see that this is 0, 0, 1. 45 minus 32 gives us 13. So this is 0, 1 minus 8, we get 5. So 1 and 0. Okay. And then second step, so this step is done. Then we want to do this step, break it into 4-bit chunks. So we start from here, we take these 4, we take these 4. Okay. So then we convert this into decimal. Okay. So what is that in decimal? That's going to be 8 plus 4 plus 1, which is 8 plus 4 plus 1 will yield 13. And then here, if we take this 0, 0, 1, 0 and look at it just as a 4-bit number, not with these weightings, we look at it as 1, 2, 4, 8. This is simply the number 2. So we have 2 and 13. So we have 2 and 13. But as we know, 2 in hexadecimal is going to be 2, and 13 in hexadecimal, as seen over here, is D. So as we see, 45 in decimal has become 2D in hexadecimal. Okay? So just to go over the steps once again, what we've done, we first converted the decimal number to binary. Right? We got 45, we got this binary number, and then we break it into 4-bit chunks. So we take the 4 bits from the right, and then take another 4 bits. And if we have even more bits, we could just keep going on. And then we convert these into a decimal number so that we can convert it into hexadecimal. So we get the decimal number over here. We get it that it's a 2. So 2 in hexadecimal is going to be 2. 13 in hexadecimal is going to be D. So we put them together in the same order that they've come in. So 2 is on the left, 13 is on the right. Then we keep it the same way. So we get 2D. That's it. Okay. So nice and easy. We'll go ahead and do maybe 1 or 2 more examples. So if I take the number, let's start with a little bit of a larger number and see how hexadecimal conversion can be useful and how it minimizes the size of the number. So if we take a look at the following, if we have 300, okay, let's say in decimal, and we want to make this into a hexadecimal number, okay? So we have 1, 2, these are the weightings for binaries first, right? Because we're going to convert it to binary first of all. So we have 1, 2, 8, 16, 32, 64, 128, and then 256. Okay. And then we start to dissect this. So 1 goes into here, 300 minus 256. You're left with 44. So 0, 0, and then 1 here minus 32 is equal to 12. So 0, 1 minus 8, you get 4, so you're left with 4, and then you put a 1 here, and then minus 4, you're left with 0. So this is zeros. Okay? And let's say I take this right here, copy it, and we're going to work on this part. So once again, the next step is we need to break it into 4-bit chunks. So we take 4 bits, 4 bits, and this will be another 4 bits. Even though we only have 1, we'll just have trailing zeros here. Okay? So once again, if we take this, put the weightings 1, 2, 4, 8, 1, 1, 0, 0, we see that this is 8 plus 4, which is 12. Okay? Keep this in mind. This one is going to be 2, and this one is going to be 1. Skipped a few steps just because it's getting a little bit redundant at this point. So we have 1, 2, this is the first, second, and then 12. But 12 in hexadecimal, as we know, as we've seen, is C. Okay? So this is going to be 1, 2, C. And that is how you write 300 in decimal converted into hexadecimal. And you see, as the number grows and grows, we can represent it in a compact manner instead of having a large binary number such as this one with many digits. You have a 3-digit number that represents a large value, and that is why hexadecimal is very useful, and it is used extensively in computer programming and digital systems because it provides a compact way to present binary numbers. Since one hexadecimal digit corresponds to exactly 4 binary bits, it's much easier for humans to read and write large binary numbers by converting them into hexadecimal format. Okay, so finally, just one more thing, just to show you a way to check your answer once you're done. If we take 1, 2, C here, right, we know that hexadecimal is a base 16 number. Okay, so the weighting on this one is 16 to the 0. The weighting on the 2-digit is 16 to the 1. The weighting on the 1-digit is 16 to the 2. Similar to how if you have a number like 152, this is the 10 to the 0 digit, so the 1's digit. This is the 10's digit. This is the 10 to the 2's digit, right? Same way in binary, you have like 2 to the 0, 2 to the 1, 2 to the 2, so on and so forth. So if you take this and you multiply it, you get 1 times 16 to the 2 plus 2 times 16 to the 1 plus, I'm just going to delete this right here. And then you have C, which is 12 times 16 to the 0. And if you add this up, you get 16 squared, which is 256, plus 2 times 16 to the 1, which is going to be 288 total. And then you have plus 12, which is going to yield 300. And as you can see, we have now converted from hexadecimal back to decimal. And as you can see, these two values are equal, and we've gone ahead and checked our answer. So that is decimal to hexadecimal conversion for you.